We want to emphasize here in part two again, the left and right hand behavior. As we approach the limit, we have three options here. One option is to approach it from the left. That's what this negative sign is, this negative exponent here. That's the left-hand side. The right-hand side is the positive power on this number down here as x approaches c, or from both sides. And to finish an idea that was started in the last one, here is an absolute value problem, which if you plug it in, you get 0 over 0. If you plug your 0 in, you get 0 over 0, which is indeterminate. And indeterminate means to keep factoring, keep trying. So we split our absolute value into two parts. We split it into the negative x over x and the positive x over x, which gives us negative 1. Y equals negative 1 is one side of the graph, and y equals positive 1 is the other side of the graph. So let's look at this according to the negative left side of 0. Our line right here, x equals 0, comes down. Only thing existing to the left of that is the y equals negative 1 graph. So that is the left-hand behavior for the limit. Now limit is y, limit is output. So this is the level, the y level that we will end up at as we approach 0. Turn it around, what if we approach it from the right-hand side of 0? In that case, it's x over x, which is 1. So from the right-hand side, the limit is 1. If I approach it from both sides of 0, that would be the original problem up here from both sides of 0. The limit does not exist, D and E. Let's take this idea, does not exist limits. There are several cases. The first is unbounded. In fact, several are going to be unbounded. And unbounded is usually when I have functions with x in the numerator and x in the denominator. These are hyperbolas, they're hyperbolic, like the one to the right, which is the graph of 1 over x. As we approach 0, oh, by the way, we have a vertical asymptote and a horizontal asymptote in hyperbolas of this type at y equals 0 and x equals 0. So as I take the path of the function, which is right here, going this direction, down this direction, and over here is coming in towards 0, x is 0, and then towards 0 it goes up. This 0 from the left side is down here, negative infinity. Now we're approaching x equals 0 this way, and then staying on the path, you go down forever, that's negative infinity, and then on the right side of 0, you go up as you go towards 0 forever to positive infinity. From both sides, we would say they're different limits. Negative infinity is different than positive infinity. Then we would say it does not exist. Here's another graph. It's basically the same thing, except we emphasize here the number 2. If you plug 2 in here, you get a 0 in the denominator, which means undefined, which means the vertical asymptote is at x equals 2. You can see that in the drawing. There it is, x equals 2. And the horizontal asymptote is still y equals 0. So again, let's take this and as we approach, in this case, 2, positive 2, from the left side, we follow this path right here. As we approach it, we're forced by the path to go down to negative infinity on the left side. On the right side of 2, we're forced to go up to positive infinity. From both sides, that's the original problem, the limit does not exist because the two limits are not going the same direction. Let's see this again with the 2 minus x squared. Notice now the vertical asymptote is still x equals 2 and the horizontal is y equals 0. Because of the squared in the denominator, the graph looks a little different. It looks like going up and going up. So let's run through this again. As we get close to 2, we end up going to positive infinity on the left side with the negative there, and the right side to positive infinity, and together the limit, which is the original problem, is to positive infinity. They're both going to positive infinity. So they agree on that. So here's some rules for unbounded. The first is what we just did. The left and the right limits do not agree, so it's a does not exist. I call that DUI because of the test of whether or not you've been driving under the influence. You have to put your finger on your nose and your left hand finger on your nose, and if one hits your forehead and one hits your chin, you're going to have a DUI. So those are DNEs. Number 2 here we just did several examples of unbounded from the left and the right, typically a vertical asymptote. And the last one we didn't do, and you can do that on your own, it's called an oscillation. And this is an example of that. Put your graphing calculator into radians and do the sine of 1 over x. That'll be an example of an oscillation. And also, without spending a great deal of time, I want to state the limit rules, the limit operations, when f of x has a limit of L and g of x has the limit of m. We can follow the add and subtract rule here, the multiply rule, the divide rule, and the power rule. So I won't go into those, but those are the rules of operations that they operate limits by. Last thing I want to do is a comparison of 3 graphs to emphasize limits. As we find out on this one, it's all done. If you plug in the 1, substitute it in for x, you get 2. And really this is just a straight line graph with an intercept of 1 and a slope of 2. And this point, 1, 2, is just a point on the line. As you approach from the left or the right, the limit is 2. A second one that we want to do also approaches, x approaches 1. This one's a little more complicated. When I plug 1 in, I don't get a nice number like 2. I get 0 over 0, which is the indeterminate form. This indicates the problem needs to be reduced. In our case, we can see it needs to be reduced by factoring. So we factor x squared minus 1 into x plus 1, x minus 1. And notice that this cancels. This sometimes is called a curable. You can cancel this, and you get x plus 1. And now you come back. You took a little detour after the determining was indeterminate. You reduced it. Now you get back on track, and you plug in the 1 again, and you get 2. So this is the same straight line the other one was. The difference is this point 1 was in the original problem, was in the denominator. It was not canceled out yet. That means the denominator cannot be a 1. So we would say this is a curable in that this is a x equals 1, 2 is a hole in the graph. As you're drawing it, you actually lift your pencil, go on the other side of 1, and continue the drawing up to the right here. So draw, lift your pencil, draw again. Another comparison, much more complicated as it looks, is this function. It's a cubic over squared, x towards 1. Plug in the 1, you get 0 over 0 again. That means it's indeterminate. That means it reduces. So let's reduce it. You may remember how to reduce 4 terms. You group by 2's, and greatest common factor in the first group is x squared, and the greatest common factor in the second group is -1. The denominator also factors nicely. You'll notice here the way the numerator is rewritten is x squared minus 1 times x minus 2. You'll notice the denominator has the x minus 2, and those cancel. That's a curable. You'll also notice that the x squared minus 1 will factor even more, and the remaining denominator, x minus 1, is going to cancel with that, and I end up with x minus 1 equals 2. And this is the same one we had before. So here's the line, x minus 1 equals 2. Okay, we got that moved out of the way. So this turns into x plus 1 equals 2, which is the same as we had a while ago. Now you'll notice here, because we canceled x minus 1, which actually was a part of the original denominator, even though it canceled, we put in that place a hole in the graph. And we also had an x minus 2, which is x equals 2, where there was a hole in the graph also. Now if these had not canceled out, they did cancel out. When they do cancel out, you just put a hole in the graph. When they don't cancel out, you put a vertical asymptote in their way. A vertical asymptote means it totally changes the graph. Okay, so the last one we're going to do is a graph that is piecewise defined. You'll notice that at y equals -2 is this graph right here. Y equals 1 is this graph here. Y equals 3 is this graph here. But you'll notice these don't go on forever. They're just limited. Think of the time of the day from -4 to -2, and then they're done. And then the second one starts at -1 but doesn't include it, and goes to 2, that's this one, -1 open to 2 closed, and then we go from y equals 3 up here, from 2, doesn't include 2, it's open, to 5, which is closed. So I'm going to put these as limits. I'm not going to rewrite f of x every time because it's too much work, but I do want to approach it from the -1 left side. So you'll notice I drew a line, this is not an asymptote, where x equals -1, and on the left side, the only thing that exists is this one at -2. Right there. Now, when I put it -1 from the positive side, the only place that exists is right in here. This graph isn't there. This graph isn't there, just this one. So the limit, the y direction, is 1. And then if I go from both sides, -2 and also +1, well, we don't agree on the limit. That is a D&E, does not exist. Let's do that with +2 over here. X equals +2 would be a line right there. From the left side, the only thing that exists is this one. So that answer is 1. And from right of 2, this is +2 here, this one exists, only this one. None of these exist over there. And so as we approach from the right, going this direction, see we're going from the right, we're going this direction, towards 2, we expect the limit to be 3. From both sides of 2, we expect the limit to not exist, D&E. So this is an example, part 2 of limits. Some of the limit operations were in there. Some good examples of unbounded, where we go to positive and negative infinity. And here where we have the broken stair-step graph and left and right side behavior. Hope this helps you. This is part 2.